So today we're going to be talking about forces and motion, and specifically about Newton's three laws that explain forces and motion. So here's a stop action shot of a bowling alley. And for the moment, those bowling pins are standing upright and they're not going anywhere. And they will stay like that until something happens. And in this case, the something that will happen is that ball will keep going and will hit the pins, at least some of the pins. It will knock a pin flying, which will fly into another pin. And with any luck, all of the pins will go down, although it does look like maybe this one right here is going to stay standing because nothing is going to hit it. Unless this pin swings around and knocks it over, it will stand upright just like it was before the bowling ball came down the lane and hit everything. There's a lot of physics and forces and motion at play in a bowling alley. And so we're going to take a look, use that as an example in a lot of our cases to figure out what makes an object move. Well, Isaac Newton was the person who first at least thought and wrote down his ideas on what makes an object move. So the very first thing that his first law that he explained is called the law of inertia. And this is exactly what we saw with these bowling pins. An object that is not moving, or in other words, is at rest, will stay at rest or will stay still until it is acted on by an unbalanced force. By the same token, an object that is moving will stay moving until it is acted on by an unbalanced force. So the law of inertia, inertia meaning something that is not moving, will stay not moving until something happens. So these bowling pins aren't moving until the ball hits them. Go back and look at the scene of these bowling pins. Once that ball does hit them and sends them in motion, how do they stop moving? What stops them from continuing on in motion? Because that's what the law of inertia says. If it is moving, it will stay moving until an unbalanced force acts on it. You can see an example right here. This pen is going to keep moving until it hits the wall. And the wall of the lane here is going to exert a motion, an action, a force, push back on that pin and send it flying in the other direction. And it will keep doing that until it hits this wall over here. And then whatever this part of the bowling alley is called, that comes down and sweeps it back, will exert another force on it, and it will drop down into the well there until the force, the other piece force, picks it back up and sets it upright again. So the law of inertia will tell me that these bowling pins will stay still until the force of the ball hits them. They will keep moving until the force of the wall of the bowling alley lane pushes back on them and sends them flying in another direction. Eventually, gravity will pull on them and pull them down to the floor. And then the force of the floor pushing back will keep them balanced out and they will stay still. So this idea of the unbalanced force everywhere you are, there are forces that are acting on you. Gravity is pushing down. If you're standing up on the ground, the earth is pushing back up. Otherwise, if it was only gravity, you would keep going right down through the ground. So when we are sitting still, our forces are balanced. The forces that are acting on us are balanced. It takes an unbalanced force to make us move. So what is a force? A force is a push or a pull acting on an object. All motion is the result of a force acting on an object. This boy on his scooter is using the force of his pushing foot to move the scooter forward. So he pushes back and the scooter moves forward. Let's think about all the forces that are acting on this scooter. Gravity is pushing down on the scooter and the boy to keep them on the ground. The applied force is the force his foot is using to push the scooter forward. And friction between the wheels and the ground, the surface that the scooter is on, slows the scooter down. So if he gives a really hard push with his foot, that will overcome the inertia of the gravity pushing down, the earth pushing up, the friction that has slowed his wheels down, and that will send his scooter forward. We use arrows to show forces in a diagram about motion. So notice that the arrow pointing in this direction, it shows me which direction it is applied. So a force is a vector. A vector has both size and direction. So it is really critical that I show which force has the most magnitude, which is the greatest force. I show that with a longer arrow. In this case, the applied force of him pushing forward overcomes the friction that is pushing back so that he can move in this direction. So when you see a graph or a picture that shows you the motions or the forces that are acting on an object, you'll see both direction and length. And that tells you which is the greater or the lesser force. So the law of inertia says that if an object is stationary, if it is still, it is being acted on by opposite and balanced forces. And we're all aware of gravity, which pushes down and keeps us standing on Earth, not floating up in the air. But is not as evident that the ground is also pushing up. So that is the one that is one we can't see or really feel. We can feel gravity if we jump up. We can feel it pushing us back down. If we're in a car, we can feel when the car suddenly stops. We can feel our body keep going. And then when our body hits that seatbelt, we can feel that seatbelt pushing back on us. So, but this idea of the ground pushing back is a little bit hard to understand. But it must be true, because if not, gravity would keep pushing us right down through the earth. So, and we know that doesn't happen. So whenever you are just sitting still, in a chair, gravity is pushing you down. The force of the chair is also pushing back up on you. So going back to our idea that all motion is the result of a force acting on an object, to make the scooter move forward, we have to apply a force greater than the force of friction pushing back on the wheels of the scooter. So friction pushes back, we have to apply a greater force to make the scooter move forward. And that is how we unbalance those forces. If the boy stops pushing, eventually friction will slow down, push back against the wheels and slow them down, and he will come to a stop. He has to apply a greater force in the opposite direction to overcome the friction and start the scooter moving again. So how fast will the boy go? This is the idea of acceleration. So acceleration, when we're thinking of a car and we press on the accelerator, that in that instance, to accelerate means to go faster. But be careful, because when we are talking about physics and science and the laws of motion and forces, acceleration means a change in speed or direction. But right now, we're going to be thinking about it. It is going to mean how to move, how to overcome the inertia. So we talked about the boy having to push hard to get started. This scooter doesn't weigh a lot, so his force that he uses doesn't have to be tremendous. It has to be enough to overcome friction and to overcome the mass or the weight of the scooter. A heavier scooter would be harder to accelerate. He would have to push harder to get it moving and to keep it moving faster. This is so obvious to us. We don't really need the idea to understand all the ins and outs of force equals mass times acceleration to know how much we have to push a car, how much harder we have to push a car to make it move than we have to push a scooter to make it move. We understand that. We get ourselves down low so that we can push as hard as we can. We move it with our entire body. We get our shoulder down there. If you've ever tried to push a car, you know how much force it takes and that you have to work much harder to push that car to get it to go than you do a scooter. In the same way, if you wanted to, once you got that car going, if you wanted to make it stop, you would have to push back really hard in order to make the car going, because once that car starts moving, that heavier mass means we have to apply a much heavier force to make it stop than this boy just putting his foot down on the ground to stop his scooter. So this makes a lot of sense, but we're explaining how it works. So how it works is that the greater force is needed to move a heavier object and make it speed up or slow down. So the second law of motion tells us that the acceleration of an object, a change in its speed, depends on its mass and the force acting on it. And mass is the scientific term for the weight and the gravity that is pushing down on it. That's why we use those terms differently. So the mass and the force acting on it. So Newton's second law of motion tells me that this bowling ball is going to take a lot more force to get going than this beach ball, which is much lighter. And that makes sense. I wanted to throw a beach ball up in the air. I can hold it in one hand and just give it a little tap and up it goes. I'm not going to be able to do that with a bowling ball. Likewise, if I want to send this bowling ball down the alley to knock over some pins, I will have to use a lot more force. And when it goes down there, it will be going faster and it will knock over a lot more pins than I could get this bowling ball, this beach ball to go down there. If I use the same force, because its mass is so much lighter, it will not accelerate as fast. And it will not have as much force behind it to knock over the pins. So the SI unit, and that's the International System unit. So the unit that we use to measure force is called a Newton, named of course after Sir Isaac Newton. And it is the force to cause a mass of 1 kilogram to accelerate at 1 meter per second squared. So a Newton equals 1 kilogram times meter per second squared. The most important thing that you need to know about this is generally that is the measurement that we use for a force. And then we're going to actually look at where this is used to calculate forces and mass and acceleration. So to be sure that you understand, when we are talking about acceleration in physics and the forces in motion, acceleration is the change of an object's speed or direction. And this is a very critical distinction so that you should not get confused about just thinking of it as accelerating being to speed up. That's the way we use it in everyday life. But in physics, it is a change of an object's speed or direction. So it could be slowing down, or it could be meaning turning one way or the other. So let's look at some examples of acceleration. On this carousel, it might accelerate, meaning change its speed when it's just starting or slowing down, but it is constantly accelerating because it is constantly changing direction. And if you are riding on the carousel, not only are you going around in a circle and accelerating, you are also going up and down. So you are constantly in a state of acceleration, even if you're going at the same speed on a carousel. And this example of the race car, even if they are going at the same speed around this racetrack, they're accelerating in this meaning of the word because they are constantly changing direction.
And I actually think that race car is a great example, because if you've ever sat in a car, even on like the highway or a regular road, and you took a turn pretty fast, you can feel yourself being pushed or pulled towards one side of the car. And that is that is that force continuing. You're wanting to go in the same direction, but the car has to exert a force to change you into a new direction. And that's what you're feeling when the car turns.
Right. Yeah. So Yes, and so there is anytime you have the change in direction, yes, your body is, that's an example of inertia because your body wants to continue going in that same direction, and you have the force of the car pushing back on you and changing the direction that your body is going in. It's, if you've ever been in a car when it stops suddenly, the car accelerates because it stops suddenly, but your body does not. It keeps going until something acts on it, and hopefully it's your seatbelt that is keeping you from flying out of the car. So even though the car stops, your body keeps going. Some force has to, the force may have acted on the car in terms of the brakes, but it didn't act on your body. So your body keeps going until it meets a force that changes its acceleration. So this person in free fall, a skydiver, jumping out of the plane, she is going in the same direction, which is down, but her body is accelerating as she continues to fall. And the yo-yo is, even if it's going at the same speed, it's not slowing down, but it's going up and down on the string. That's a change in acceleration. So then we come to Newton's third law. For every action by a force, there is an equal and opposite reaction. So when that ball went down the bowling alley and hit those bowling pins, they bounced around, they hit each other. That was the opposite reaction. So bowling ball comes down the alley, hits the pin. The pin actually pushes back some on the bowling ball, but not enough to stop it. Maybe to slow it down a little bit. And then more that force, that unbalanced force of the bowling ball being so much stronger, sends the pin flying because the mass of the pin is less. So it goes flying. So here are some examples of equal and opposite reactions. The reason a rocket goes up into the atmosphere is the force of all that fuel pushing down on the ground. And that opposite reaction sends the rocket up into the air. That lift comes from the push down of the fuel on the ground. This is the example of the person sitting in the chair. So gravity is pushing down, but the chair is pushing up on the body. We would not be able to walk if the ground did not push back on our feet to give us the lift that we need to move forward. And when these two objects come at each other and they hit, which one has the greater force? If you get a good solid hit on a baseball, the baseball stops and changes direction, and that is the equal and opposite reaction going forward. So then I looked at some of the GED questions to get an idea of what you might or what you might see on a test. And here's one that we didn't actually talk about, but knowing what you know, I think you can figure this out. So it says that mechanical advantage, MA, is a measure of the force amplification that is achieved by using a tool, mechanical device, or machine system. The formula for mechanical advantage is, and it ended up being up here. So mechanical advantage is output force divided by input force. Now, I could go back and read that whole thing again and try to understand what it's saying. I'm going to go down here to the question that was right after this little explanation. A crowbar can be used to remove a nail from a board. Now, I know a crowbar is a kind of a lever. It's got a little fork in it, and if you press down on it, if you stick that underneath that little fork underneath the nail and then press down on the other end, it will help to lift the nail up from the board. So if the crowbar has a mechanical advantage of 8 and the force of 40 newtons is applied to it, what will be the output force? This is just using math to solve a physics problem. And I don't really need to understand every single thing that is up here in this explanation if I know that a mechanical advantage is a measure of force, and it's telling me that this mechanical advantage is 8. I know that I could think of there being an 8 here, and the force of 40 newtons is applied to it, and I put 40 here because it's asking me what is the output force, and I'm going to use that to be X. Now let's see. I put that on my board here, and I say the mechanical advantage is equal to the output force divided by the input force. I know that the mechanical advantage is 8, and I'm looking for the output force, so that must be the X. And it tells me that the force of newtons, 40 newtons, is applied to it. I know that applying something means it would be an input. So I would come out with an equation that looks like this. So I have the mechanical force is equal to the output force divided by the input force. And then I substitute in my values. I know it tells me in the problem that the mechanical advantage is 8. It's asking me what the output force is. So I know that must be my unknown, my X. And there we go. It told me that my applied force was 40 newtons. Now, how do I solve this? This becomes a math problem. How do I solve? Well, what this is telling me is I'm going to take some number and divide by 40, and that number will be 8. So I can think of my problem as being some number divided by 40 equals 8. How do I know what that some number is? Well, if I told you that some number divided by 2 equals 6, you would say 2 times 6 is 12. So 12 divided by 2 equals 6. In this case, I'm going to say the exact same thing. Some number divided by 40 equals 8. Well, if I multiply 8 by 40, I will get that number. And the answer is X equals 320. Okay, so let's go back and look at our screen again. So if a crowbar has a mechanical advantage of 8 and the force of 40 newtons is applied to it, what will be the output force? Well, the output force would be 320 newtons. So that's a problem that we solved by understanding math and knowing about substituting values into a formula. Even though we weren't totally sure what force amplification meant, although we know that amplification, if you have an amplifier, it's making the sound louder. So force amplification must mean strengthening of force. So that makes sense to me that I put in some force, I apply some mechanical force, this output force must be greater because I'm amplifying it. And 320 is greater than either of those. So that's awesome. So then another one that we saw, another GED problem, was use Newton's second law to find the initial acceleration of an object with a mass of 42 kilograms when a force of 6 newtons is applied. For this problem, we're going to ignore direction because we know that that's an important part of acceleration. It has both speed and direction, and round to the nearest 100. So again, they've given us the formula. Newton's second law is force equals mass times acceleration. And we're being asked to find the acceleration. So I need to substitute in for these two variables. Force, they tell us, is 6 newtons. And the mass, they tell us, is 42 kilograms. So now I just need to substitute in to find my answer. So while I'm doing that, you take a minute and do that. And let's see if we come up with the same thing. So I took my formula, force equals mass times acceleration. I substituted in what I know, that the force was 6 newtons and the mass is 42. And if I solve for A, that will tell me what is the acceleration. Again, if I know that one number times another times 42 is 6, how will I figure that out? I'm going to take 6 and divide it by 42. I'm going to undo that multiplication. So 6 divided by 42. Let's see what. Yeah, I know that's might be unusual because you're dividing a smaller number by a larger number. And we don't always do it that way. And it told me to round to the nearest 100. So when I say 6 divided by 42, I get 14 hundredths. And what unit should I be using here? Let's see if we can figure this out. Acceleration. What would be a unit for acceleration? In this case,
do you want me to answer, or did you want?
yeah, do you know? That would be great.
I assume it will be meters per second squared.
You are correct. Meters per second squared.
And that's because you told us earlier that the acceleration is a newton is accelerating 1 kilogram at 1 meter per second squared. And so this was newtons and kilograms again. So we can use that same measurement of meters per second.
Beautiful. That's right. And that, yes, acceleration is measured in meters per second squared, and or which means that the meters is the distance used and it's divided by the time, second squared. So one more question from the GED. Two objects on Earth are dropped from the top of a building that is 70 meters high. Object A has a mass of 12 grams and object B has a mass of 6 kilograms. Assuming there is no air resistance, which object will hit the ground first? So I had to think, well, I have no idea what 12 grams, what might weigh 12 grams. So I looked it up, and it's a AAA battery is 12 grams. And 6 kilograms is a little bit more than a bowling ball. I guess it depends on how heavy your bowling ball is. But it's about the weight of a bowling ball. So if I drop a AAA battery and a bowling ball from a building that is 70 meters high, which is like about 210 feet, which object will hit the ground first? So the answers could be the battery, bowling ball, or they will hit the ground at the same time. And the key to this question is assuming there is no air resistance, because the force of the air pushing back against the bowling ball is different from the force pushing back on the battery. And if there is no air resistance, if the only force acting on the objects is gravity, then the acceleration of both objects will be equal. They will hit the ground at the same time. So that is very counterintuitive, but it has to do with this formula we were just working with. The force equals mass times acceleration. So if the force is the same, even if the masses are different, the acceleration will be the same, and they will hit the ground at the same time. Interesting. That, I think, is a very non-intuitive answer. When we drop them, because air resistance will make a difference, which one will hit the ground? I'm not sure I know the answer to that. Do you, Chris?
It would depend on, so it depends on which one the air resistance
More.
and the volume affect more. So volume increases faster than surface area does.
Mm-hmm.
So the battery would probably be affected more by air resistance in the same way that like a penny is affected more by air resistance than like a silver dollar. The volume of the internal increases faster than the surface area, and what air resistance is pushing back against is how big the object is, the surface area of the object.
Yeah, I was thinking the example that I know the best is like using a feather, and I know the air resistance of a feather is much greater. So that's
Right.
why it wafts down slowly, or why leaves waft down slowly.
But you know what? They've actually, NASA has done a very cool thing, and I wish I had this video queued up. but NASA has something called vacuum chambers. And
Yeah,
those are rooms that have no air in them whatsoever. And
right.
so I encourage any student watching this, after you finish this video, search for this in Google, NASA vacuum chamber gravity. And what they've done is they've done the bowling ball and the feather in a vacuum chamber where there is no air resistance. And they do hit the ground at the same time when it's just gravity pulling them.
It's so counterintuitive. We
Yeah.
just, we just don't believe that it will happen.
Yeah, we're so used to air resistance because we feel it everywhere. You feel the wind, you feel
Yeah,
if you stick your hand out the window of a car, you feel the air resistance. We're so used to it that, yeah, it is very counterintuitive.
yeah. So I think this is the kind of question that unless we think clearly about that and understand that air resistance is a force which is going to act on both objects um, in a different way, so that this is easily a question that could trip you up. So looking for that key of no, only the force of gravity pulling down on it, it will pull down at the same with the same force on both objects. So this last question is, again, it's about acceleration. So a stopped speedboat increases its speed from a rate of 0 meters per second to a rate of 45 meters per second in 3 minutes. What is the boat's acceleration in meters per second squared? So it gives us a formula and we just have to substitute in the information. So we're looking for acceleration. So what we're going to substitute in is going to be in this position and in this position. And it tells us change in velocity. We're starting at 0 and we get to 45. And then it tells us change in time, 0 time to 3 minutes. Now, here's the tricky part, because this is in minutes, and yet our units are in seconds. So we need to change our 3 minutes to seconds. And this is what it's going to look like. We start with our change. Our rate is 0 to a rate of 45. So 0 minus 45 meters per second. And then our 3 minutes. We start at 0, but because we're using seconds, we have to change that 3 minutes to seconds. So 3 times 60 seconds is 180 seconds. We say 0 minus 45, we get negative 45 meters per second. 0 minus 180, negative 180 seconds. And then we just do our division. And you may know that if we divide a negative by a negative, we'll have a positive answer. You don't know, you substitute that into your calculator. Your calculator will do that for you. So negative 45 divided by 180, negative 180 equals, whoops, here we go. Is it under there? I'll let that go away. Fine. Was that answer in there and I just didn't see it?
I didn't see it either.
Okay. Was this thing in the way? This little, can you see the, there you go. Can you see that thing that's
The
where my,
control?
yeah, there we go.
Yeah, oh, there we go. Aha.
Yeah. So it's 2,500 meters per second squared, and see where this down here is divided by seconds squared. And we know that is the unit for acceleration. So that makes sense. So all we needed to do was treat this as an algebra problem where we have an unknown, which is our acceleration. Then we needed to know about how to note change in velocity, because we could have started from something other than zero. If this boat had already been moving, this might not have been zero. If it had a speed of 15 meters per second to get started, then we would have had a different answer here. Or it could have been decreasing its speed. So we could have started at 45 and gone down to 15. So that's why this is looking like a subtraction problem. We have to say what the change is. So we're starting at some speed and then subtracting the new speed that we go to. The change in speed here, the change in time here, we're starting at 0 time and going to 3 minutes. And remember that you would have gotten a very kind of normal looking answer of 45 divided by 3, 15. I bet you that's one of the answers in a multiple choice question. And you would have been very satisfied thinking, oh, there's my answer. Pay attention to your units and make sure that you have changed your units to be what they need to be. And that is probably the trickiest part in this whole problem. So if we do that division, then we come up with the answer of 2,500 meters per second squared as the acceleration rate. Okay, and that's all I have on forces and motions, and I hope that was helpful.